Okay, Unit 1, Atomic Theory. Now you're going to want to copy all of this into your notebook, and you can use the spacebar to start and stop as needed. I'm sure I'll be going faster than you'll be able to copy this down. Now it's going to be really important that you use one notebook and include all of this into your notebook. You're going to have to do your homework in there, everything in there. Part 1, Discovering the Atom. Now, as we go through these notes, you're going to see this little triangle every time we start a new topic. So I strongly encourage you to have some sort of symbol or some way to indicate that you're starting a new topic. When I used to take notes, when I was a student, I would always draw a straight line across and leave kind of a space. So I mean, maybe put the date in, so kind of indicating that we're moving on to something new. Our first topic is the history of atomic theory. 2,500 years ago, Greek philosophers believed that all matter is made up of earth, fire, water, and air. And what you're listening to is a song from back in the 70s called September from a group called Earth, Wind, and Fire. And of course, they got their name from this. I know that's in Spanish, but I kind of like that picture. So this is called September, Earth, Wind, and Fire. Get it? It's a great song. I bet you've heard it. If your parents have, ask them. Democritus, Greek philosopher, lived 460 to 370 BC. Now, I'm not real big on dates, so don't worry about that too much. But you should have a sense of when these things happened. So this is over a couple of thousand years ago. He was the first to propose that matter was not infinitely divisible. Now, what do we mean by that? Well, imagine that you had a rock and you cut it in half, and then you cut it in half again, and again, and again. Could you just go on forever? Well, Democritus said no. He said eventually you would get to a particle or a piece of rock where you would not be able to cut it any further. Now, it's important to note that this was just philosophical conjecture, meaning that they were just thinking about these things. There was no evidence to support this idea. That's what Greek philosophers did, specifically or particularly for the physical world. They didn't do experimentation, they just thought about it. Kind of funny when we think about it now. Now, it wasn't until a couple of thousand years later that we really made any progress. And this is John Dalton. He's an English chemist and physicist, 1766 to 1844, and he's considered to be the father of our modern atomic theory. Now, for hundreds of years prior to John Dalton, there had been experimentation, and we were able to separate out different elements like gold and silver and tin. We knew that oxygen existed and hydrogen existed, but we didn't know what made those substances special. Why is gold gold? Why is oxygen oxygen? It was John Dalton that kind of put all of the experimentation that had been done for hundreds of years into a coherent theory. And this is called John Dalton's atomic theory. This was 1803. Okay, so we're going to list his key ideas. First, matter can be explained in terms of atoms, from the Greek word atomos, indivisible. So it was John Dalton that gave atoms their name. All atoms of an element are identical. So if you had a sample of gold, say, with the particles that make up that sample of gold are all identical atoms. If you had a sample of silver, well, it's made up of identical atoms of silver. And if you were to compare an atom of gold and an atom of silver, they would be different. This was brand new thinking. Atoms cannot be divided, created, or destroyed. Atoms combine in simple whole number ratios to form chemical compounds. So, for example, water is H2O, 2 hydrogens for every 1 oxygen. It isn't like 3.5 hydrogens and 2.7 oxygens. It's whole number ratios. Carbon monoxide is 1 to 1. Carbon dioxide is 1 to 2 ratio. In chemical reactions, atoms recombine to form new substances. So, for example, iron reacts with oxygen to form what we call rust. Now, iron is quite different from oxygen, which is quite different from rust. So this is a new idea, this idea that the substances or elements combine to form compounds that too have specific whole number ratios. But are atoms really indivisible, really atomos? That was one of Dalton's ideas. It took nearly 100 years to answer that question. So John Dalton's theory was at the beginning of the 19th century, and we have to go to almost the very end to answer that question. In 1898, an English physicist named J.J. Thomson conducted experiments using an electrical discharge tube called a Crookes tube. And this is what a Crookes tube looks like. Now, what it is, it's an evacuated tube, which means that all the air has been sucked out of it, and you have electrodes on either end hooked up to a battery. And what he found was that if the voltage was great enough, you would see a beam of particles going from one side to the other side. Now, this is the cathode side, and it was propelled to the other side, which is the anode. So let's watch a little video on this.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thomson, who became the director of this, the old Cavendish laboratory. In 1896, Thomson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates, across which you can apply a voltage, and they hit the end of the bulb here on a screen which glows so you can see the beam. Now this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thomson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thomson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thomson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. It might parody Shakespeare, say my use is great because I am so small.
Okay. Thomson concluded that all elements give off the same negatively charged particles. He called them cathode ray particles because they emanated from the cathode part of the Crookes tube. Now, he tried many different elements, but he found that regardless of what the element was, gold, silver, tin, carbon, always got exactly the same particles. So it must mean that these particles are in common with all atoms, all elements. Today we call these particles electrons. Thomson devised the short-lived plum pudding model of the atom. And in the plum pudding model of the atom, you have an evenly distributed positive charge, that would be the blue portion of this diagram, and merged within it are the electrons, negatively charged. Now, this would be a good diagram to include in your notes. I'll try to mention which diagrams are more important than others. You can copy everything down if you want, but I'll try to make note of when you should draw a diagram and when you shouldn't. So before you start copying the diagram, you might listen for my heads up on that. Okay, now, however, this model was shown to be completely wrong by one, by one of the most important experiments of all time. It changed everything. And by the way, plum pudding is, can you think of it like a lumpy pudding? So you have this positively distributed region with electrons, kind of like plums within a pudding, negatively charged. Okay, so that brings us to Ernest Rutherford, a New Zealand-born English physicist. 1871 to 1937, considered to be the father of nuclear physics. The Rutherford gold foil model, 1911. Rutherford's gold foil experiment, 1911. And he used it to test the plum pudding model. Was it correct? Okay, now this diagram here, I'll ask you to kind of hold off on copying it down right now. We're going to see a video in a second, and then you might want to go back and copy this diagram down. And what it is, it's a simple representation of the experiment that Rutherford did. This is a lead box containing a radioactive source which shot out positively charged particles. Today we know of those particles are alpha particles made up of protons and neutrons, 2 protons, 2 neutrons, but back then they didn't know that. They just knew they were very small and had a positive charge. And what he did was he shot these particles at a very thin layer of gold foil and saw what happened. So let's watch the video on this.
What you see here is a recreation of the Rutherford experiment. He used an element named polonium, which gives off positively charged particles. Now, you put the polonium into a lead box, something like this. It has a small opening in it. This is a lead barrier. It has a tiny hole in it that will allow only a thin beam of positively charged particles to pass through. There's an opening here, and then here is a very thin piece of gold foil. Surrounding the gold foil is this ring, which is specially coated with a material such that when a positively charged particle hits it, it gives off a flash of light. All right, now what do you think would happen if those positively charged particles hit the gold foil? Well, Rutherford thought they would pass right on through the foil and hit the ring about right here. Boy, was he in for a surprise. Now, here's what actually happened.
Most of the particles passed right through the foil and hit the screen behind it, but not all of them. A few were deflected sideways, and about 1 in every 20,000 of them bounced off the foil back towards the source. Rutherford was astonished.
It was about as credible as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
What was deflecting some of the particles? Rutherford calculated that each atom must have a nucleus, a center with a large mass and a positive charge concentrated into a small volume. The nucleus had to be massive enough to deflect the heavy particles bombarding it. And since the bombarding particles have a positive charge, the nucleus must have a positive charge to repel them. So once in a while, a particle would closely approach the nucleus and bounce back. But the majority of the particles passed right through the negatively charged electron clouds.
Okay, so you might now copy this diagram down. You should have a sense of what it represents. Okay, so let's move forward. Okay, so here we have the plum pudding model and alpha particles being shot at it. Now, Rutherford, as you just saw, expected the alpha particles should pass straight through the gold foil undeflected, if the plum pudding model was correct. But that did not happen. Some alpha particles deflected bounced back. So how could that be? Everything within the atom should be allow the alpha particles to pass through. The alpha particles would be much larger than the negative electron, or than the electrons. And remember that the bulk of the atom, the positive distributed charge of the atom, the electrons can move around within it, so it must not be solid. So alpha particles should be able to just go right through. But we had deflection. Rutherford concluded that nearly all the mass of the atom was located at its center, which he called the atom's nucleus. So we have deflection taking place. Now note that most of the particles pass straight through, but every now and then it would hit something so massive, so solid in comparison, it would just bounce right back. Okay, so Rutherford concluded that the atom must have a very, very small nucleus where almost the entire mass is located. And the nucleus must be very small with a positive charge because the alpha particles had a positive charge. If it had a negative charge in the nucleus, it would be attracted to it. It wouldn't bounce away from it. Rutherford called the positive particles that make up the nucleus protons, from the Greek word protos, which means first. The neutron would not be discovered for another 20 years. Now we know that the nucleus is made up of both protons and neutrons, but all that Rutherford concluded was that the entire mass of most of the mass of the atom was in the nucleus, and he just assumed that they were all positively charged particles that make it up. Neutrons, as we'll find, have no charge. Rutherford's model, not to scale, often called the planetary model of the atom, where electrons orbit the nucleus like planets around the sun. So here's the nucleus and the electrons moving around it. Rutherford's model completely changed our concept of the physical world. It showed that atoms, matter, everything is composed almost entirely of empty space. So you have this very, very small nucleus and the electrons orbiting it. In between the electrons and the nucleus is nothing. About 99.9999, I think it's like 11 or 13 decimal places of nothing. A good analogy for the size of the atom. If an atom's nucleus was the size of a pea and placed in the middle of a football field, its electrons would be out in the parking lot with absolutely nothing in between. So when we think of an atom, like Dalton thought that it was a solid particle. Well, it's far from it. Almost the entire mass of the atom is in the nucleus, and the electrons, which are much, much smaller, reside very, very far away. Now, question. If atoms are mostly empty space, why don't they just pass through one another? How is anything solid? So you might think about that for a minute. Atoms are almost entirely empty space. The electrons are really small. So if one atom comes near another atom, why shouldn't they just be able to pass through each other? What are the chances an electron would hit one another, or the nucleus would hit one another? Well,
now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy, because if it's mostly empty space, they should pass right through one another. But what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields. When the electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now, this means that I'm not really sitting in this chair at all. The atoms of my body are about 1 angstrom hovering over the atoms of this chair.
An angstrom, by the way, is 10 to the negative 10 meters, so 10 billionths of a meter is an angstrom. So to answer the question, there is a repulsive force between the electrons of atoms that prevent them from coming into direct contact with one another. This gives the illusion that matter is solid. Now, electrons are negatively charged, so there's a repulsive force. They want to get away from each other. So when we think of atoms coming into contact with each other, well, they too want to get away from each other because the electric fields from the electrons repel. However, there was a big problem with Rutherford's model, and he knew it. If electrons travel in orbits around the nucleus, they should lose the energy needed to remain in orbit. Specifically, a charged particle accelerating in what's called angular acceleration, for example, in orbit, should lose energy. You experience angular acceleration anytime you're driving in a car and somebody takes a sharp turn. You're kind of leaning over to one side. That's angular acceleration. Well, when charged particles do that, they should lose energy. So what keeps the negatively charged electrons from crashing into the positively charged nucleus? So the electrons, if they are traveling in an orbit, they should lose energy. And so they should quite quickly crash into the nucleus. Now, of course, that doesn't happen. But why not? That question will be answered a little bit later in this unit. So that's the end of today's notes.